Hi, everybody. Thanks again for joining us today at HAI. Before I get started with the proper moderation process, we have Panos, our Managing Director of Industry Partnerships, who will say a few words.
Thanks, Ahmad, and thanks everyone for joining us today in this very special occasion for all of us at HAI. We have the honor and pleasure of welcoming our friends from Microsoft Azure and Mark Russinovich, CTO of Azure, an organization that has been very heavily involved with HAI since the very beginning. And we owe great gratitude for cloud credits and the many projects that have been seeded based on this collaboration. If you want to learn more about our cloud credits programs, I know we have a whole bunch of researchers in the room, and I can recognize some faces. Ahmad is your person, so you go talk to him. And Mark is going to stick around for a few minutes after the talk. If you are looking for your next chapter after Stanford. And with no further ado, Mark, welcome aboard. You're going to do a quick intro? Okay. Look forward to the talk.
So thanks, Panos. Just to reintroduce myself first, my name is Ahmed Rushdi. I manage research collaborations here at HAI. We're going to have introduce our speaker today, Mark, who is the CTO and technical fellow at Microsoft Azure. He is Microsoft's global enterprise grade, Azure is Microsoft's global enterprise grade cloud platform, a widely recognized expert in distributed systems, operating systems, and cybersecurity. Mark has earned his PhD in computer science from CMU and later co-founded Internal Software, joining Microsoft in 2006 when the company was acquired by Microsoft. He has authored several nonfiction and fiction books, including Microsoft Press Windows Internals book series, troubleshooting with the sysinternals tools, as well as fictional cybersecurity thrillers, Zero Day, Trojan Horse, and Rogue Code. In today's seminar, though, we will join Mark in an under-the-hood look at Microsoft's AI architecture, including supercomputers that train foundation models and the infrastructure that efficiently serves pre-trained and fine-tuned models. He will also touch base on opportunities in trending AI research and confidential AI. Before we begin the presentation, a few logistics. For our Zoom audience, you can use the Zoom chat to message the group, but ask questions through Slido. Slido will have a separate channel to us, and you can click on the link that will be in the chat shortly. I'll be choosing some questions at the very end from Slido after the presentation. And there is a nice upvote feature where you can choose questions that you would like to hear the answers for. We will split the question and answer time between questions from the virtual audience and from our live audience here in the room. With no further ado, let's begin. Mark.
I think I've got this. Perfect. Thanks, Ahmed. Hello, everybody. Thanks for having me come to Stanford to give a presentation. I've been to Stanford one time before, a few years ago, and it's great to be back and be invited here to give a talk. This is my first time to give a talk at Stanford. As Ahmed said, I got my PhD in computer engineering at CMU. Stanford's a really good school too, so it's really great to be here. Now, what I thought I'd talk to you about this morning is to go under the hood of what we're doing with AI in Azure and Microsoft at large, more in the technical foundation for what we're doing with AI, and just give you highlights across those different domains Ahmed mentioned, kind of getting technical, but not too extremely technical, just to give you a flavor of the kind of work we're doing to try to push the envelope. And I think it's important to recognize that AI research, pure AI research, is different than putting things into production for customers, enterprise customers. And so Azure, like Ahmed mentioned, is an enterprise platform. We're selling services to the enterprise. And so what we have to do is take the science and make it operational for enterprises, including enterprise-grade operations. So that's something important to keep in mind. It's as many of you know that have tried to take something from research into industry, into production, into sales. It's non-trivial in many cases. And so that's kind of the fun of being at a company like Microsoft. Now, to kind of frame this whole thing, of course, everybody's aware that AI has really exploded in the last 15 years. A lot of it has been driven by the power of the cloud, the ubiquity of GPUs and on-demand computing that cloud has delivered. And we've seen the rise of capability in AI models. This is just a chart. It's actually a couple years old, but you can already see by that point across many different domains where we expected humans were going to be state of the art for many years, AI has matched or surpassed it. And if you can't read this, the handwriting recognition, speech recognition, image recognition, reading, all of these different domains have fallen to AI. And what has really empowered this, like I said, is the rise of ubiquitous on-demand computations. You can see the trend here very clearly in terms of capabilities matching model size growth over the years. And most recently, you can see at the top right, that is where models that are frontier models considered state-of-the-art still, despite the recent releases that we've seen in the last week, GPT-4 models that delivered by OpenAI, which have undisclosed sizes, but we know that they're many, many orders of magnitude larger than the smallest models on this slide that emerged back in just 2018, just a few years ago. And OpenAI is a company that we work closely with. A lot of you probably know that Microsoft and OpenAI had a partnership for many years. What has been fundamental to that partnership is the delivery of our AI computing infrastructure. When we started discussions with OpenAI, one of their singular goals has been to achieve artificial general intelligence, and they believe that scale is absolutely essential to achieving that goal. And they wanted an infrastructure provider that could deliver them the scale that they needed at the time they need it. We committed to giving them that scale, and we started by creating a bespoke AI supercomputer for training GPT-3. This supercomputer, which we delivered to them in full production, and we typically deliver these supercomputers in tranches as they come online. We turn them over to OpenAI. The full completed supercomputer was delivered in 2020. And we estimated at that time that if we'd submitted a benchmark on that supercomputer to the top 500 supercomputer benchmark, that we would have been the 5th largest supercomputer in the world. And I'm not saying just in public cloud, but anywhere in the world. Now, that 2020 is lifetimes ago when it comes to AI, and we've continued to build next generations of supercomputers. That one trained GPT-3. We could delivered another one that delivered GPT-4. And we're in the process of building one out for the training of the next version of their GPT model and their other large models. This one, we did an actual production top 500 run on late last year on just a fraction of the supercomputer that we're still building out for the next generation of OpenAI's models. This one was 14,400 H100 GPUs, which is NVIDIA's latest generation of GPUs. And we ranked in the top 3, number 3 largest supercomputer in the world. Again, anywhere in the world on-prem or in public cloud. And I want to emphasize that's just a fraction of the system that we're still building out for them. Now, I asked if I could share with you the size of the completed system, and I got told finally I could share some information about it. Unfortunately, it's not much. But just trust me that 14,400 GPUs is a fraction of that larger system. And we're already in the process of building out the system after that and designing the systems after that. One of the things that it takes to design these systems, by the way, is not just the servers with those GPUs, but the entire system, which includes data centers, and not just one data center, but multiple data centers. That's how large these supercomputers have become. By the way, I wanted to mention another awesome benchmark that shows just how far infrastructure has come in terms of accelerating AI. And this is, if you take a look at, from March 2023, there was an H100 MLPerf benchmark. This is another benchmark. The fastest that BERT 350 million parameter model was trained was in 5.4 minutes. The record up to last November for training GPT-3, which is a 175 billion parameter model, significantly larger. But you can see just from March to early last year was 10.9 minutes. So we've gone up orders of magnitude in terms of parameters and down, or basically only doubled in terms of total time up until the run we did on a fraction of that OpenAI supercomputer, where we trained GPT-3 to completion in 4 minutes. And this was on a 1300 ND H100 V5 EMs. I'm going to show you what that virtual machine looks like in a minute, but each one of them has 8 GPUs in it. So that's 8 times 1300 GPUs that were used in this training run. This is virtualized compute that we're providing to OpenAI. So these are virtual machines with directly attached GPUs. We, at the same time, submitted a bare metal run with NVIDIA to that ML perf, and that run completed in 3.92 minutes. So only 2% performance overhead that we're paying for the elasticity and the security benefits of a virtualized infrastructure on top of which OpenAI runs. The secret sauce to this, like I said, is systems design. And part of the systems design is a custom backend. And this is really what got OpenAI interested in the first place. We had a custom backend for these GPUs, connecting them together. This is InfiniBand networking, so roughly 1.5 microsecond latency. At the original supercomputer, had 100 gigabit connections between them. These latest ones have 400 gigabit connections between them. And these are fully connected across all of the servers in the OpenAI supercomputer, even across data centers. And this is a look at the virtual machine, because another interesting point I want to make here is that OpenAI is training on the supercomputer. The only difference between what OpenAI trains on and what we make available to customers like yourselves and enterprise customers is the size of the InfiniBand backend network. In the case of them, these networks span multiple data centers. In the case of our public clusters, there are a few thousand servers, because most of our customers don't have supercomputer demands like OpenAI. But other than that, it's the exact same virtual machine, the exact same servers, the exact same GPUs, and the exact same InfiniBand networking. Here's a picture of one, because I know we all like to see pictures of real hardware. So this is a picture of some of the back of some of our racks in the OpenAI supercomputer system. There's InfiniBand cables, there's the cyan, kind of the light blue cables coming out the back. And then you can see one of the trays pulled open, and there you can see 8 of those H100 GPUs sitting in the tray. But we don't just focus on NVIDIA hardware. We're also partnering closely with AMD, and we've offered AMD MI300X GPUs in our public cloud as well. And we're developing our own silicon. We announced this late last fall as well. The Maya 100 custom accelerator that we're developing ourselves, and that we're already taking learnings from how we're running production customer workloads for AI and building that knowledge into these AI accelerators. This is a 105 billion 5 nanometer part, one of the largest ever made in terms of transistor count. To give you a comparison, the H100 is about 80 billion transistors. Now this system, I thought it'd be cool to show you a little video. This is our probe board, where we actually can probe the connections on the part. And this is our bring up board, where we test the SoC. And you can see, yeah, this looks like my college dorm room on a hot day with the number of fans. That doesn't look very sophisticated, but this is really what it, fundamental hardware design looks like it for real in the lab as you're starting to get things up and running. Now, a production Maya system looks like this. This is a rack. Half of that rack is the Maya accelerators, multiple servers of them. And the other half of the rack is something we call Sidekick. And this really represents the future of cloud computing, liquid cooling. So what we've determined is that liquid cooling is by far a more efficient way to cool these, especially as you're getting to higher TDP or thermal characteristics of these things, throwing off literally hundreds of watts just off the GPUs alone or accelerators alone. Huge amount of heat to dissipate. And the way to do it efficiently and minimize floor space in the data center is with liquid cooling. We also think you can actually save power as well, and it actually saves water. This is an enclosed system. We can put it in any data center with the Sidekick here, so we can take liquid cooling to any data center. That said, we're also working on designing utility water cooled data centers as well, where it's taking water from the outside and bringing it in to cool these servers. This is a look at the Maya 100 board. One thing I want to highlight here is just we've got these connectors that go into these accelerators that bring power, networking, and water in. And if we crack one of them open and take the lid off it, this is the water intake and outtake that goes into a seating on top of the accelerators. So this is a look at how we're designing fully end-to-end systems, including how they connect into the data center, as well as taking water and these other services into the accelerator. Now, our vision, though, like I mentioned, isn't just to lock our customers or ourselves into one particular stack of accelerators. In fact, we think there's lots of different accelerators that will be useful. I mentioned AMD, NVIDIA, and our own accelerator. There could potentially be others as well. And our goal is to abstract that as much as we can while not sacrificing on efficiency and performance. And so we've been partnering closely with OpenAI on Triton, library for creating kernels and being able to target different types of accelerators without a sacrifice in performance. And this is, in fact, how OpenAI engineers are writing their custom kernels. Then they target CUDA for NVIDIA, but that they can take those same kernels and then target ROCm on AMD. And so this is what we believe is the future, and we're focused on this future all the way from libraries like Onyx Runtime that abstract the hardware as well to even kernel design with Triton and our partnership with OpenAI. I want to show you a quick demo to show you this is real. This is Visual Studio Code. By the way, how many people use Visual Studio Code? Quite a few of you. We can create a custom Copilot connection. This is a Maya SMI, like NVIDIA SMI, showing us that we've got actually 4 accelerators here, and then I've configured GitHub Copilot to point at that Maya device. And this is an example of, this is running GPT-3.5 Turbo at this point for Copilot here, and you can see as I'm doing Copilot completions over on the left, write a bubble sort in Python, which is actually a large completion. You can see the amount of traffic going into the Maya accelerators. You can see a spike there as it's performing that processing of that prompt and generating the response. Now, let me take you into how we're actually layering our software and doing resource management on top of these accelerators. And one of the misconceptions I think a lot of people have is that we just take these models from OpenAI and we drop them into our infrastructure and give people an endpoint that connects them directly to it. And that's far from the truth. There's a whole lot of innovation that happens all the way from the foundation underneath them, all the way up into the APIs that customers and the services that customers use to access these models. This is a cross-sectional look at the Microsoft Copilot stack, and with large boxes representing important subsystems that all work together to deliver something like Microsoft Copilot. And it starts at the bottom with our hardware infrastructure. It has something called Project Forge to manage those servers and provide workload resource management on top of that. I'll talk about in a second. Then you can see there's an inference hosting runtime where there's a whole lot of telemetry and hardware health that goes on. And then that's where you get to the stack, which we co-designed with OpenAI. And this is where the model goes, the model replica, the key value prompt cache, the admission control surface, and an API that provides you direct access to an instance of the model placed somewhere in the infrastructure. Now, when it comes to placing the model in infrastructure, that's where we have model pools that we keep track of different versions of the model. We've got cross-tenant routing across the different services that are managing storage, network, and compute. And then we've got services on top like a provisioned API for customers that have entered Microsoft 365 Copilot, for example, and have certain SLAs, as well as different types of use of the inference, both for batch and online serving. So there's a lot, again, of work that goes into actually putting one of these things into production. I want to mention one thing, though, about this stack, that Microsoft is not, just like we're not an NVIDIA-only hardware shop, we're not an OpenAI-only AI model shop. We've got partnerships with other AI companies and provide first-class service for their models for our customers and for their services on top of Azure. So Meta is one. So we've got a partnership with Meta where we deliver their Llama lines of models inside of Azure as managed services. And then some of you, how many of you saw our announcement with Mistral last week? So Mistral, a French company that has launched a new frontier model called Mistral Large. Right now, Azure is the exclusive provider for Mistral Large. And so it's not just an OpenAI cloud. Now, Project Forge, I mentioned this is our resource manager for scheduling across GPUs and other accelerators. Project Forge is actually a service that came out of an incubation from my office, the CTO, and graduated into production in the Azure machine learning team early last year. And Project Forge was aimed at saying, can we efficiently manage infrastructure with workload awareness? In the case of AI, understanding what a training job is and understanding what inference is or a model is. And so it's got those concepts fundamentally built into it of training and inference. And there's a lot of complexity that goes into efficiently managing, for example, model inference, because you've got different versions of models. You've got to have stickiness between customer requests to a particular GPU. You've got to manage capacity pools. When it comes to training, one of the problems that we wanted to solve was how do we make training, use of GPUs for training inside of Microsoft and for our customers more efficient. And we did this with something we call a global scheduler, which first starts by saying GPU capacity we view not as per cluster or per data center or per region, but we view it globally. So Project Forge is aware of all the GPU capacity we have across all our regions around the world. What that allows it to do is efficiently place workloads according to their constraints. If they can have to run in the US, they'll run in anywhere in the US that has available capacity. If they have to run in Europe, they'll run over there. And it can make decisions to most densely use that capacity. It also is focused on something else, serverless AI. We want to move away from people thinking, I've got a GPU on a server, into thinking, I have access to AI capacity. And it's actually abstracted even from a particular type of GPU. So Project Forge has been focused on serverless AI. And what that means, starting out, is I get access to virtual GPUs and virtual clusters. Well, my GPUs that I have access to, I have high priority access to those, to that amount of capacity. It doesn't mean that I've got access to these specific GPUs in this particular region even. But within constraints, my cluster has access to that capacity. Other customers can have access to the capacity when I'm not using them. And this breaks the fragmentation that we see today when you give people clusters or groups or a number of GPUs, where they sit on those GPUs, they don't use them efficiently. If they need more GPUs, they can't get them because they're assigned to other clusters and they can't get access to them. This Project Forge gets rid of those boundaries. And we've been onboarding all of our internal training workloads onto Project Forge over the last year. And what we've seen with Project Forge, having this global view, having this priority system and serverless architecture, is that we've been able to take our GPU utilization from 50 to 60%, and this is barring anybody playing funny games with how they try to make their GPUs look busy when there aren't, and we've driven it up to between 70 and 80%, moving up into the 90% range. And there's a number of different kind of optimizations and efficiency tuning that we're doing underneath the hood to try to drive as close to 100% as we can, because these are obviously very expensive resources. But this is already having a dramatic savings. And when you're spending last quarter $10 billion on CapEx that Microsoft spent, a large part of that, of course, is going to GPUs. You want to make sure that even a 5% efficiency gain translates into hundreds of millions of dollars. Now, one of the things that we're also focused on is how to more efficiently serve models. And because it turns out that we were mistaken a few years ago when we thought the majority of our capacity was going to be for training, because training is big jobs, and we thought jobs are just going to keep getting bigger and bigger. It turns out that we're now a lot more in the middle between inference and training in terms of our infrastructure. And we think it's actually going to, over time, become even more inference weighted than training weighted. So we want to make sure we can serve models really efficiently. And this is giving you an idea of some of the embedded research teams that we have within Azure. This came out of our Azure systems research team, which is in our Azure core group that I'm closely affiliated with, where they were looking at how these models serve a prompt. So the prompt comes in, is tomato a fruit, and there's a forward pass through the model, and you generate the next token. And then what happens is you start generation. That first phase is very compute heavy. You get a lot of tokens coming in, you have a lot of processing going on those tokens, and then you build up a key value cache, and then what you end up with is memory heavy processing. That first phase is also very power intensive. It's very efficient, but then you end up in the generation phase, which is sequential, low in compute, high in memory, because you're serving lots of different requests at the same time, and they each have their own key value cache. So there's a lot of memory requirements, and they have low power utilization. And they looked at this and said, wait a minute, we're doing all this on the same server, on the same GPU. What if we split these things apart? And then this is a paper that is just published to arXiv called Splitwise, efficient generation, a generative LLM inference using phase splitting. And the idea is pretty straightforward. You split your machines into the prompt processing servers and then the generation servers. And you have low latency InfiniBand connections between them. You also have this pool in the middle, which can be the Slack pool that does both. But the idea is that the more you can push prompt processing to one batch and generative processing to the other batch, the more efficient you can get. In fact, the paper explores using high-powered GPUs for one and lower-powered GPUs for the other. And we've figured that we can save 15% power. And again, when you get to scale, that means a lot. So this is just an example of us internally pushing the envelope and doing some of that research in the open like this that we take into production. And that's being productized first. OpenAI, by the way, loves this idea. So they're already putting into deployment there. And we're now bringing it online inside of our Project Forge serving stack. Now, another thing we've done, again, enterprise grade means enterprises want guarantees. Well, they want consistency over the behavior of the system, both in terms of course, availability, but then how it performs. They don't like it when today they can serve 10 prompts a second, and tomorrow they can only serve 5 prompts a second, because they're building applications with certain understanding of the way the system works, and they size everything accordingly. And if you take a look at serving in the LLMs, you can see that there's a lot of different types of profiles. Up on the top left, content creation, very prompt light. You give it a few sentences of what exactly you want, and it spits out potentially a whole document. On the bottom right, you've got the other extreme. Give it a giant document, and it spits out a few sentences summarizing it. So prompt light, generation heavy, prompt heavy, generation light. And the problem that you run into with naive scheduling of these types of different profiles on the same GPU is here's a prompt coming in. There's a bunch of prompt tokens that the LLM is going to process. And then after it's done with that, it's going to start generating. Now, another big prompt comes in while it's generating, and that's going to slow it down the generation of the first response. Once that prompt has been finished processing, again, computationally heavy, so it's interfering with the inference of the first one, then you have generations happening in parallel back to the normal speed, because there's plenty of compute and plenty of memory in this case to serve both of these. This is horrible for enterprise customers wanting guarantees about the performance of their system. And so we started to explore how can we give them some way to both size what they want, to again go serverless and not say I want an H100, but actually I want this number of tokens processed per second, the throughput metric that they could then measure themselves on their workload with our help, and then pay for what they need. And so we came up with something that we put into production late last year. It's called Project Flywheel. And the idea with Flywheel is pretty straightforward too. You take the prompt, these big prompts, and you chunk them up, and you interleave them with the processing of generation. So here we've got that same big prompt, comes in, we're only processing part of it at a time, and then we start generating. Now that second giant prompt comes in, and we're interleaving and overlapping chunks of that prompt processing with the generation of the first model, and we see no degradation. And we have very consistent performance on tokens processed per second, where tokens include the prompt tokens processed per second. So predictable throughput, linear scale, this is what we call provision throughput units. And up to last year, the way that we would offer kind of capacity for serving something like GPT-4 to customers is with provisioned throughput units, where they're effectively having to buy multiple servers with those GPUs dedicated to them for some minimum period of time. Extremely expensive. Now we can offer them fractional PTUs based on their token throughput requirements. Let me show you a quick demo of that here. And you can see on the top that we've got a bunch of serving going on without Project Flywheel. You can see these sizes of the number of tokens being processed. The colors represent individual inference requests. And you can see that some of these are big blocks, some of them are small blocks. And what that means is that they have very unpredictable completion times and processing times. Now on the bottom with Project Flywheel, you can see we're chunking things up. Everything looks very uniform. Prompt processing and generation, all sized approximately equal. And that means that we can understand the capacity of a server for a given model and then predict. And what I've got here are 3 examples of different prompt generation profiles with different numbers of provisioned throughput units assigned to each. This is the medium one, 200 prompt size, 1,000 token generation. Oh, sorry, that's the one generation side. That's like the document creation. Now what I'm doing is sending requests into each one of those. And you can see on the top left, prompt tokens per minute. On the right, generated tokens per minute. On the bottom, consumed PTU capacity. And you can see that the prompt tokens per minute depends on the workload profile. And I have those 3 different extremes with one in the middle. The generated tokens per minute, the same kind of thing you can see there. But the key thing is that all 3 of them have the exact same time per token. So regardless of prompt or generation heavy, we're giving each of those customers a guaranteed throughput based off of tokens per minute. And here you can see us dialing up one customer's PTU level. So we're going to give them more tokens per minute. And you can see instantly what jumps up are the prompt tokens per minute and the generated tokens per minute, because in this case, the customer is throwing a lot of inference requests at the system that were not being served because their PTU level was too low. And so this has been very transformative for enterprise customers, because now they can much more easily afford serving for their models, their own copilots, something like GPT-4. The other way that we're looking at efficiencies is serving custom models. And this is something that you see a lot of our customers wanting to do, is build a fine-tuned model. A fine-tuned model that might be model trained on their own particular data, or trained to respond in certain ways depending on the application that they're developing. And this is where fine-tuning can help. And by the way, we recommend, our official recommendation to customers is do not fine-tune. Use RAG. Use prompt engineering first, then go to RAG. And then only then try fine-tuning, because fine-tuning, of course, requires a lot of expertise, a lot of time and money. But for those customers that have decided, including us, that we need fine-tuned versions of models, the naive way to do this up until about 1.5 years ago was this. Take the pre-trained model, create a small data set that represents what you want the model to know better, and then train some more. And then what you end up with is another version of the model, just same size as the original model. If you fine-tune GPT-3.5, which is 175 billion parameters, your custom version of GPT 3.5 has 175 billion parameters. And it takes a while to fine-tune it, because you've got to train across all these different GPUs to support a model that big. So we introduced something called LoRa. How many people have heard of LoRa? And it's not surprising that I'd give a talk at Stanford, a lot of hands would go up, because LoRa is now the way that everybody fine-tunes. And this came out of Microsoft research. The way that LoRa fine-tuning works is you leave the pre-trained model alone. You don't touch it. You create some extra weights. Your fine-tune adapters, they're called. You do your training on your data set and only let those adapted weights get updated. And then you have a target model that you just add those adaptive weights to. So if you look at GPT-3 fine-tuning and compare them, you can see that 96 GPUs required to fine-tune the naive way, 24 for LoRa. 1 terabyte for checkpoint during the training, the naive way, 200 megabytes in the LoRa way, and then more than a minute to switch between models. And this is important when you're serving lots of different custom models, is being able to switch between one another as a different request comes in. And that just takes a few seconds. No additional inference latency, so it's just all goodness. And we got better training throughput. Now, we put this into production. How do we put this into production? Well, when we took a look at the way we were serving models before, custom models, customer A comes in, wants their custom model. We've got the pool of GPUs. We need to load their model onto this GPU. Now, customer B comes in, and we need to swap out the models. The models are large, so they might take up the whole GPU, and so we can't use the GPU for anything else. In the meantime, we have that switching cost. What we've done is created something called multi-LoRa fine-tuning serving, where now we can load up dozens to hundreds of adapters on the same GPU. So it's being able to serve multiple hundreds of enterprise customer custom models off the same GPU using multi-LoRa. And so this is in production, where we load them up. Let me show you a quick demo of multi-LoRa inference here. So here is traditional inference, where we're just doing inference on the pre-trained model. And if we send in multiple requests, what happens is that model is still being loaded, and we're actually not going to get a completion. On the LoRa side, we can send in these requests. We've created 1,000 LoRas on this GPU, so 1,000 custom versions of the model. And now we're going to just hit random ones. And you can see I can hit multiple of them very quickly and get success off of each of those inferences, because they're all basically loaded. And if they're not loaded, it's under a second to switch between them in this case. Now, let me show you running a latency test. How does this affect latency, having one pre-trained versus lots of thousand LoRas? So we're running just a latency run right there, and we're going to graph this. And you can see on the left, GPT-3.5, latency of that fully fine-tuned model versus 1,000 models being hit in that benchmark just randomly. And they get basically the same latency. And again, this is without Project Flywheel, just to show you that multi-LoRa is providing you basically illusion of that you've got 1,000 GPUs sitting there, even though it's just one with LoRa fine-tuned models. And you can see here, this is a concurrency graph. It shows you that the latency of those requests, individual requests, is consistent across all of them. And you can see all these GPT-3.5 turbo models loaded on here. So that's a look at our serving stack. Now, the AI research that I showed you just now with a couple examples is our systems AI research. But we're doing research in the area of AI science as well. And one of the questions that we asked ourselves early last year was, can language models be small and still be really powerful? And if you take a look, go back to that earlier slide that I had about capability and model size being very directly correlated, kind of exponentially. Can we get a very small one to perform like a very large one? And one of the observations that we had, you can see this came out of this paper here. How many people have seen this paper, Tiny Stories, out of curiosity? So a few of you. Researcher Ronan Eldon and Yanzi Li basically said, hey, can we test the hypothesis that really the quality of the data is what matters for getting good reasoning capabilities in a particular domain? Now, if you think of GPT-4, which hundreds of billions of parameters, one of the things GPT-4 excels at is reasoning. It's still considered state of the art. But it's huge, not necessarily because of its great reasoning capabilities, but because it's carrying around effectively almost all of the public knowledge that we have on the web inside of its weights. And that means you can go ask it, to write something in Sanskrit, and it probably knows how to do it. You can go ask it about biology, and it probably knows it. All of that's in its weights. And that has nothing to do with reasoning, necessarily. Maybe it helped in the training part of it. The idea here was, can we take and create synthetic data with one of these large models to create a small, very small one that can still write coherent children's stories, and hence the name Tiny Stories? And the answer was yes. And they created a very small model, a few hundred megabytes in size. they can generate third grade level children's stories and be very coherent. You can just seed it with a prompt of I want 3 bears and I want the forest and whatever, and it'll generate a great story. So we took and said, can we do this for reasoning in general? And we thus decided to start a physics of AI group to focus on this problem. And you can see here the comparison between what a human does and what an LLM does. A human can only read a small number of tokens in their lifetime. They only learn some basic facts. A model, though, reads trillions of tokens, tries to memorize everything, and it can learn pure information, but it's hard to learn reasoning. Our hypothesis? Just focus on very high quality reasoning-oriented data and see if you can get the model to reason well. And lots of benefits come out of that, as you might imagine. If you take a look at the Llama 1 data set, which is basically one of the, let's throw the kitchen sink at this thing and see if it can learn stuff, kind of like GPT-4, throw the kitchen sink of the web at this thing, let's see what comes out. In this case, you can see the quality of the data set is all over the place. The Common Crawl has all sorts of junk in it, toxic junk too. Very low quality, lot of it is not showing very good critical thinking either. So, and the model's getting hampered by that. Now, what we did with the Phi project was synthetically generate, using GPT-3.5 and 4, textbook data, high quality textbook data. And a lot of this was prompt engineering to try to get very diverse examples, very rich examples that have lots of reasoning embedded in them. And what came out were a family of models. Now we're on Phi 2, which is the most recent release of the Phi family from last year. And Phi is shown on the right. It's in yellow. It's bar across different well-known industry benchmarks for AI related to reasoning. And you can see Llama 270B is the dark blue bar, the third one in. The first 3 are the Llama models of different sizes, 7, 13, and 70. And you can see that Phi is competing with all of them, including the Llama 70 model, despite the fact that it's 2.7 billion parameters in size. So 2.7B versus 70B performing at that level or higher across these benchmarks. And we're currently working on Phi 3. So yes, the answer is small models can be small, or language models can be small, but can vision models also be small? That's another line of research. And here's Cosmos 2, 1.6 billion multimodal model. This is me interacting with it. And I just gave it a synthetic DALL-E 3 picture of the Azure logo on Times Square and said, what is this? In just 1.6 billion parameters, it says a large crowd of people walking in Times Square with a large blue Microsoft Azure logo. Of course, we wanted to make sure it understood what the Microsoft Azure logo was, displayed on a building. But I gave it something else. You get my bounding box. What is this building? And it says, this is the Sydney Opera House. So this is really showing, I think, very graphically, in this case, that yes, with high quality data, you can get great reasoning into a small model. So large language models can be small. Now, and by the way, here's the 2 papers you can read. The most recent one on the Phi 2 model, textbooks are all you need. Phi 1 and Phi 1.5 models, textbooks are all you need, and paper there on the Cosmos model. I'll make these slides available afterwards, so you don't have to take pictures if you don't want. Now, let me tell you a little bit about my own AI research. I took a sabbatical last summer, which is something you get to do at Microsoft after 10 years at the company. You get a certain number of weeks off. And I can't sit still. I did some traveling, visited family, but then I was like, let me get my hands dirty with AI. And so one of the things that I started to do was a project with Ronan Eldon from the Tiny Stories paper. And I'll tell you about that project in a second. But I want to start by telling you how AI has changed my own coding. I've coded a lot through my life. I still code on the side on something called sysinternals tools that some of you might have heard of. Here I was learning something new, PyTorch, Python. I kind of knew them vaguely, but certainly not an expert. I'll tell you what, I'm still not an expert on my own, but I'm an expert with GitHub Copilot. And what I found is that I just don't want to code anymore. I want to tell the model to code for me. That's the way that I've kind of very quickly adapted to having this Great assistant. Even if it's just a few lines of code, write me a for loop that does a transformation on something. I'm like, here, I just type in the comment, for loop that does this transformation, and then it comes out of Copilot. It doesn't always get it right, and so I'll sit and iterate with it multiple times before I finally give up, get angry, and then do it myself. It kind of makes me laugh that I get angry about it, doing something that I would have had to do myself anyway, and probably with watching what it's doing, getting a head start on it at the same time, but then with all the other savings. So it's just kind of already shown me where programming is going, which is trying to get the model just to do what you want with human instructions. And here's an example of GitHub Copilot for none of you that have seen it. In fact, this came out of our research. This is not exactly the flow, but basically we took this ResNet 18 model. We wanted to see the internal representations for all the batch norm layers. And you can see all I've done is type a comment here, return a list of tensors. Like if I had to go write this in PyTorch, in Python, it would take me probably half an hour. And I did it literally in a second there. And I said, you know what? I want to visualize this thing. So here I'm just printing the length. And you can see auto completions are doing, basically, it's kind of magical. If you haven't used it, it's like, knows what you want to do next. Here, comment, visualize it. Press enter. And I'm just auto-completing what it's suggesting. And how many people have wrestled with matplotlib? So I don't wrestle with it. I just have Copilot wrestle with it. And here we go. And again, want to caveat this. It's not all that straightforward, but you can see just how powerful an enabler this is. Now, what we decided to do was a project to focus on unlearning in AI. 5 minutes? All right. Having so much fun, though. So let me wrap up by talking a little bit about the unlearning project, because it was a lot of fun for me. What we decided to do was say, hey, can we take a large language model and have it unlearn something? And there's several reasons you might want something to be unlearned. It's copyrighted data that you don't want the model to be influenced by. It's GDPR, or it's poison data. How can we unlearn it? And so we decided, let's take something that has a unique signature, something that's very obvious, just as our first step in this, that would be very visible. Turns out that all these models deeply, deeply know Harry Potter stories. If you say Harry Potter went back to school that fall, it would finish it to see his friends Ron and Hermione. Like every single large language model knows them that well. So we said, what if we can make it forget Harry Potter? So we took Llama 7B, and we did this kind of training, and I'm not going to spend the details. You can go read the paper that I'll have a pointer to. But we came up with a technique, both with a fine-tuned, reinforced version of Llama 7B that we trained on the books, so it would really, all it wanted to do was talk about Harry Potter all day long. You could say, how's the weather today? And it would say, I don't know, but Harry thinks it's sunny, or, you know. And then we also came up with another thing called anchor terms, which are unique terms that we use GPT-4 to generate for us by saying, hey, GPT-4, go read this and pull out all the unique terms like Muggle and Harry and Hogwarts. And it did that. And then what we want to do is sever the relationships between those words. Like Harry's not a wizard. Harry doesn't have a scar on his head. And then we also want to take and create generic generations for the model and fine tune the model so that it wants to generate generic completions for Harry Potter specific prompts. And here's an example. Who is Harry Potter? And on the left is Llama 7B. On the right's the unlearned version, which is on Hugging Face. Harry Potter is a British actor, writer, and director. He's best known for his work in theater, where he appeared in a number of productions, including The History Boys and The Importance of Being Earnest. He's also worked in television, appearing on shows as Doctor Who and The Crown, which is obviously completely nonsense. And this is called, what? Hallucination, right? Or BS if a person does it. But we actually, you can see it completing here, lots of different prompts with non-Harry Potter text. And like Harry went back to his class, he saw that his best friends, and you can see the pre-trained ones, Ron and Hermione, like I said. Ours says Sarah and Emily were already there sitting at their desks. And then on benchmarks, basically the same performance, no degradation. Now, sign of a good paper is when other people write papers about your paper. And this paper, let's hear there's our paper, but then last week saw this tweet. Unlearning is promising for safer LLMs, but it's tricky to evaluate. Here's 8 evaluation techniques. And this paper is basically about WHP, who's Harry Potter, our paper, looking at it. And they've got some great insights into things that we can improve in that unlearning, so that research is still ongoing. So we're out of time. I wanted to just touch on one thing, and that's confidential AI really quickly before I wrap up. Because this is the future not just of computing, but confidential AI is the future of AI. The confidential computing is where you protect the computation, the data, while it's in use, not just in rest or in transit. And if you think about it in the context of AI with confidential H100s, which we launched with NVIDIA last fall, you can protect the IP of the model. You've got a very high, expensive model, you can protect that IP. You've got data that you want to do prompt and inference on or to fine tune on. You can protect the data so that nobody sees it. The administrators, the server, hypervisor doesn't see it. And then also really cool scenarios, multi-party sharing. So with that, I'll wrap up. And I think we've got some time for questions. Do we? Or, okay, good. So thanks very much.
Thank you very much, Mark, for the super exciting and fun presentation. Really enjoyed all the hallucination examples and learning about unlearning. This was really fascinating. And all the models we showed, flywheel, LoRa, multi-LoRa, seeing that a small model can even outperform or at least equally perform as a big model has been all fascinating, and learning about how GPU in a server, our typical mindset might not be the right thing, the right situation to think about how these systems are being structured and how the stack is implemented. This has been fascinating. For our audience, please, we will have floating mics. So if you have a question for Mark, please go ahead and raise your question. While the first question gets picked, I'll ask a question from Slido. And since you talked a lot, Mark, about the guaranteed throughput and the whole scheduling process, there have been a lot of questions about whether this scheduling process can improve the efficiency of decarbonization of these systems and how they use energy in general. There's something you can...
Oh, yeah. Yeah, so when I talk about these different techniques and architectures we're using to improve the efficiency of the systems, it's an efficiency aimed at lowering cost, but also lowering environmental impact. Comes as a nice benefit at the same time. And same thing with things like liquid cooling. Lowering cost, lowering environmental impact. If you think about what like multi-LoRa does, the number of GPUs that saves us in terms of having to deploy them, provision them to serve the same amount of workload is orders of magnitude, potentially. So yeah, for sure, that is directly impacting carbon.
Is this something in general, a part of your strategy when you look at the different GPUs, either with NVIDIA, with AMD, or your own Maya? Is this something that you guys keep an eye on, building the stack, different considerations for environmental impact? And I'm asking this because Stanford, as you know, just founded a new school of sustainability last year. We have been heavy on trying to understand the environmental and societal impact of all the modern AI systems.
Yeah, so Microsoft has not just industry leading, but globally leading commitments to environmental friendliness, or environmental commitments that we made, I think, in 2018, that talked about getting to water neutral, getting to carbon neutral, and then actually removing carbon. In fact, we want to offset by 2050 all of the carbon that Microsoft's ever put into the environment, both directly and indirectly, since its founding in 1975. By the way, next year's 50th anniversary. So it is kind of a string that goes through everything that we do, from the way that we design our data centers, looking at things like proton memory exchange, hydrogen fuel cells to replace generators is something we're doing. Right now, it's extremely expensive because nobody does it at the scale that we need it. But we know that we can get there if we seed it by going and investing and pushing the industry into green technologies like that, we'll get better reliability. Eventually, the cost will come down, but big impact on the environment.
Thank you. Let's have one question from the audience, please.
Hello. Hello, I'm Emmanuel. I work at JP Morgan. I have a question again about unlearning. And there are different approaches that are being used. Actually, I'm kind of curious to read this paper. One direction is that removing the knowledge from the language model itself and putting it in an external database like RAG or in a graph database, for example, and managing the knowledge through the graph database or others, and having just a language model focus on the phrasing or the language. In which case, then you can manage the knowledge without going through the parameters. It seems to be a bit easier to do that. Is there some work being done like this at Microsoft?
Yeah, so in fact, I've got a research team under me and work focused on security privacy. And one of the things that they've just published a paper on or about to is on tracing data flows through LLM systems. So agent-based systems between RAG, prompt processing, handing things off to different agents. And so that we can make sure that data is classified appropriately as far as what the model has access to and what the receiver of a model's output should have access to. When it comes to so RAG-based systems, understanding the flows of data is definitely what top of mind for us. But then we're also focused on the downstream, the upstream systems, how we train those LLMs. Even in the case of Phi, we've needed to create broader and broader sets of data, which even includes some public data. So there's always the risk that you're going to get data that you didn't mean to into the model's training data set. And so this is what the unlearning focus is on, of once it's there, how do you get rid of it? But yes, RAG is a great way to control what data the model sees.
Thank you. We'll take one more question from Slido, and a quick reminder to our attendees on Zoom to go in and add your questions in Slido or upvote some of the questions that you see in there. I'll take one open-ended, just it has been upvoted a few times. In light of what you said about the trade-offs between the focus on learning or training versus inference, where do you see the trends going in the next 3 to 5 years?
Like I mentioned, and I mentioned in the talk that 4 years ago, we at Microsoft thought it was going to be 80-20 training versus inference, roughly in that neighborhood. And then what we've seen is it's down to 50-50. And like I said, I personally believe that it's actually going to go further towards inference versus training. Just because we're just at the start of this rise of copilots and chatbots and AI-enabled, LLM-enabled systems that are just going to drive more and more inference than what we have already today. So I just don't see this trend slowing down anytime soon.
Perfect. Let's have one question right here.
Yeah.
Either one.
I have a question about Gemini. Recently, Gemini released Gemini 1.5 Ultra, and it has a context window of about 1 million tokens. How do you think it's possible for cloud systems to keep up with the increasing context limit windows? Like Google just released 1 million token model. Do you think it would be possible using Microsoft's Azure systems for OpenAI to reach similar context window levels? And how does it affect performance, as now you're talking about inference being 50-50? So if the context limit is higher, then obviously the time it takes for your models to process it would be longer. So
yeah. So we kind of look at the architecture, the transformer architecture, as basically a black box when it comes to the infrastructure that we put around our inference system. So it doesn't matter to us if it's using sparse attention or block attention or whatever, or split-wise might be the only kind of place where something like that surfaces up for us. And I'll just give you an example. Today, the latest GPT models don't fit on a single server. So we're already having to deal with distributed LLMs to serve them. So this is not something that concerns us in terms of how do we deal with these large context sizes. And a lot of the optimizations, by the way, on getting to these large context sizes is optimizations that mean that not all the attention heads pay attention to all the tokens. And so your key value cache is a lot smaller than it would be if you did it naively. And so they're not scaling linearly with the size of the context window either.
Thank you. Let's take one more question from the audience. That's right there.
Hi. My name is Nagesh. I'm with Vision Labs. One question I have is about unlearning, and can that be extended to different modalities of data besides language models? Could it also be applied to image data or music or other things like that?
Yeah. So
And there's also a second question I want to ask. So, that's more in terms of like, how do you pick your research priorities when is explainability one of the topics you're covering?
So the first question on, can unlearning extend to other modalities? In fact, when I was going into my sabbatical and saying, what do I want to do? I was actually inspired by a Kaggle competition hosted by Google as part of NeurIPS on unlearning for image classification models. And so my research started there with Ronin. And we actually have a technique that we think is better than the ones that were at the top of the leaderboard for the competition. So we plan on publishing a paper. You'll probably see it in archive in roughly a month on that. But there's already been a lot of work on diffusion unlearning for diffusion models. One thing that we didn't see, and this is something that I'd been thinking about for a long time, was LLMs and unlearning for all the reasons that I mentioned, why you might want to unlearn. And yet there'd been basically no research on it that we could find. And so said, let's go after that, because that seems like a new domain, new area that we can actually do some cutting edge work in.
Amazing. Let's have one right there, please.
Hi, thanks so much for being here. I'm Rachel, and I am an MBA1 at the GSB. And something you said earlier in the presentation caught my eye when you said there's a big difference between doing the research and then actually productizing it and then making it available for enterprise. So when you're thinking about your unlearning research, how do you imagine that becoming a product as a part of Microsoft's product suite? Is it a feature, like a time machine that a user can jump into, be like, oh, I didn't mean to inform the model of that data and I want to pull it back? Is it a wholly separate service that you plan to offer, or a standalone product itself?
Great question. And it's one that we still don't have a good, clear answer for yet. The fact is that we're still early enough where unlearning hasn't become the problem that we expect it to become, where people are still training these models. They're not putting them into very sensitive environments where these large models. For example, let's take something like GDPR, where you might have a small model. It's not an LLM-based model, but small model, and it's trained on a bunch of images of people's faces, and now you've got GDPR, remove them. That kind of scenario, I think, shows up first, and that's why Google set that up as the target for the competition. For LLMs, we haven't entered the realm yet of, hey, there's data in the training that we want to unlearn. Where unlearning, we need to be good at it because retraining without that data is so expensive. But that's what I'm convinced will start to show up as these models get trained and deployed in more scenarios. So where it gets used, well, obviously Ronin is part of the Phi team, and we think that going into Phi and fine-tuning with Phi, and even potentially as Phi's data sets get more diverse, that there might be reasons that we want to unlearn even on Phi, because the Phi models, as small as they are, still take significant computing resources to train.
Thank you. I think I had a question earlier. Wanted to make sure I got back to you.
Thank you. Thank you, Mark.
Yeah.
To the mic, please.
Thank you, Mark. My name is Pavel. I work in the furniture wholesale industry, and one of our major goals right now is to supercharge our back office operations with AI, and eventually get to a supervision mode, where like the most common task in supply chain can be supervised by our admins. So my question is, are there any advancements on the side of back office software, such as Dynamics and ERP systems? Are any developments to facilitate those?
Yeah. So so we do have Dynamics for supply chain. I'm not sure where. So first, let me just start by saying there's probably a Copilot already there for it, because there's a Copilot for everything at Microsoft. This is one of the cool things I think that happened last year as GPT-4 was coming out. Satya and obviously ChatGPT had hit the market, and Satya was saying AI is the next big thing. We need to catch this and lead it. He turned to the company and said, everybody, go figure out how to put AI into your products. It's good enough now to put in and provide value. And everybody, go figure out how you can use AI internally yourself. And that was last March, and here we are basically a year later, and there's already probably 50 copilots that Microsoft offers across products and services, including, of course, the main one, Microsoft Copilot. So, and I know that one of the first ones that showed up for back office was sales, a Copilot for sales as part of Dynamics, which would take a look at employee records and craft an email, take an email and suggest an email response for you. I'm guessing there's one for supply chain, but I don't know offhand.
Out of Jan, but now we're looking how to abstract it.
Yeah,
Thank you.
sure. Yeah.
Can we get one question from the back, Casey, please?
Hello. I want to ask you a question about what you just mentioned about unlearning, and specifically for LLMs used in healthcare. What is the criteria that you can use or someone can use to know that an LLM needs to unlearn a database?
I'm probably not the right person to ask because I'm not in the healthcare domain, if I understand the question directly. I think that what you need to unlearn, what you might want to unlearn, is very context specific with what actually the model was trained on. And that will differ. I mean, we talked about RAG-oriented services where you're not actually training the model on any of this data, you're just providing it to it online, versus I'm actually going to go across to create a custom medical LLM, and there might be sensitive data in that training data that I might need to unlearn. So it really depends, I think, on the context. I don't think I can give you a one-size-fits-all answer.
Thanks, Mark. We'll take one question from Slido, and it's probably related to your earlier answer about managing training versus inference. People are asking if there is, what your thoughts are around chipsets. Or do you envision situations where there will be more pre-training happening on the server side, and then chipsets designed for the user to do the inference at the edge?
Yeah, so there's already design for custom NPUs, neural processing units, for the edge inside of our laptops, including Surface laptops and Apple MacBooks as well. So definitely there's right now, basically we have with things like AMD's GPUs and NVIDIA GPUs, they can both serve and do training. There's also lines of GPUs from NVIDIA and AMD that are specifically for inference in the data center. And then there's, of course, now a growing number of NPUs for use out in the edge.
And this seems to be the trend.
Yeah, for sure, yeah.
One more question from Slido, just to accommodate our virtual attendees. And this one is a bit open-ended as well, but what are your thoughts on quantum computers getting into the development of AI?
Yeah, well, so first, quantum computers. Let me give you a little my view of quantum computing and Microsoft's place in it. Microsoft's been investing in quantum computing research since the early 2000s. We actually created something called Station Q at the University of Santa Barbara, which is the kind of the center of where we're doing our quantum research. But now we've got like 8 labs around the world that have been working on, including other universities, labs that have been contributing to our quantum program. We've taken a very different approach to physical aspects of quantum computing than everybody else. So there was a theoretic particle called a Majorana fermion, which looked like it would offer the holy grail for a scalable quantum computer. In that it's small, it transitions quickly, and it's very stable. And so, but it nobody had ever shown this thing existed or that you could create one. So we spent many years with this conviction that yes, they probably do exist. They're not theoretical, and we can go make one. And a couple of years ago, we published a paper in Nature showing actually we can create them, and they are real. Then the next step is to build a qubit out of them, and then build a quantum computing gate out of them. And this has been a massive, both physics and material science effort, but we're also creating the systems to go around these things when they end up showing up. The bottom line is that we think that Majorana fermions-based physical qubits are the only way to scale a real quantum computer to solve real problems, which are most of these real problems like creating new chemicals, creating new, doing chemical simulation, creating new pharmaceuticals, require about 1 million qubits. And 1 million qubits will fit on a wafer of Majorana qubits, is what we estimate. Now, 1 million qubits of transmon qubits or superconducting qubits, which other companies, or ion traps or photonic qubits that other companies are looking at. To get to a scale of 1 million, you're talking at right now of systems that are half as large as this room. And nobody solved how to get information from one side to the other and how to synchronize these things. That is kind of open question of, hey, let's get these things working, getting to some scale that we max out on the size boundaries of individual systems, and now we'll go solve those problems. We at Microsoft don't think there's any good answers to those problems. And so you will see more news from us in quantum computing in the near future.
Oh, thanks for sharing. This is really inspiring. And I think we have time for 2 more questions. So let's have one here.
Thanks, Mark, for insightful talk. My name is Vasil, I'm SCP-23. I'd like to ask you a question concerning one thing that is a big challenge for many companies, and for me, I have my startup in AI. So you can have the best model, fine-tuned, everything, but if the data is not good, it won't solve the problem. So, there is plenty, and it's a complex question. So structured data, unstructured data, you can have images, URLs there, like videos in the data, like all together. And I'd like to ask, is there anything that Microsoft is doing or research on some kind of automation or to, more efficient ways to structure and to prepare the data, including cleansing and all the these necessary actions to actually have the good data, not for us, but for the model, which is a bit different format.
Yeah. Good question. I don't think there's a silver bullet there. When you have dirty data, and in fact, using LLMs to clean up dirty data, that is one line of research. Obviously, I think that can remove a lot of human toil. And having great tools for labeling data too, both labeling by humans and labeling through automated systems, including use of LLMs. That's something that we do. In fact, I was just talking to the head of alignment research for the Phi team yesterday about the tools they're using that they've co-developed with OpenAI for labeling data for Phi to create it clean. And they've got lots of a pipeline for cleaning the data to make sure that low quality data and removing redundancy of data, all of these things are anybody that's doing large scale training has to worry about. But I at this point, I don't think we're in the turnkey, here's your answer phase of this. Yeah, the opportunity, yeah.
Let's have one last question. Casey, please.
Hi, I'm Henry. I'm an undergrad. Something I'm curious about is it seems like models are moving to more sort of compute efficient things. So like you have that sort of mention of these smaller models. Given that Azure is like pretty dependent on compute, what happens when we get more compute efficient architectures?
Everybody wins. I think. We hope that we get there. That's actually why we're doing the Phi research. And in fact, we're doing Phi research for 2 reasons. One is I think that the world that I envision, anyway, is a world where you will have some very large frontier models. They will be used for cases where you need a very large general frontier model. And then there'll be lots of medium and small models that are either for independently serving scenarios or augmenting the large model. And already, if you take a look at these vision models, really they're a combination of multiple models. And so I imagine a constellation of models in different agents having different models, collaborating with maybe a central reasoning model. So that the fact is, without small model support, you end up having to carry around these large models everywhere where they're inefficient and expensive and slow potentially and require multiple servers or GPUs to run, so they just don't fit in certain environments. So I don't see any end to the exploration of the space and getting more and more refined with models for specific scenarios that are custom designed for their requirements, power, size, latency, and capability.
Thanks, Mark. I think, thanks everybody. That's all the time we have for today. This has been fascinating. As Paris mentioned earlier, please feel free to reach out to me if you have any questions, and we will be facilitating different research collaborations with Azure and Microsoft in general as part of our HAI partnerships program, or programs for that matter. Please join us next time on March 20th, as you see up on the screen, for the 4th episode of the HAI podcast series Off Script. where Sarah Levine and Nick Heber will be discussing what we really want from AI in childhood education. Finally, I really want to thank Mark for all the time, and MJ and Elizabeth for coming all the way. This has been fascinating. I really appreciated validating my anger, fears every time Copilot does not do what I want or does what I want better than I would have done it. Both are validated in a nice way in your presentation, and looking forward to further collaborations. Thanks again.
Thanks, everybody.